In terms of who I am, my name is Michael Paul. I work for the University of Lincoln. I'm a business development manager at the University of Lincoln, but my background is in industrial design and technology transfer. And I work very closely with our School of Architecture and the Built Environment, our School of Design, Film and Media Production. I also work very closely with the School of History and Heritage, English and Journalism. I work with industry to help our academics engage with industry. But I've got a particular background in industrial design where I've grown up with 3D printers, 3D scanning, etc., etc. So I'm going to talk about the 3D scanning and 3D printing and how we've used it working with or supporting industry through the University of Lincoln, and particularly two of our consultancy teams, Lincoln Conservation, who work in the heritage sector predominantly, and Design Block, who we work closely with our county council, our local county council, to provide services to industry around new digital fabrication techniques for a range of industries, manufacturers, etc., etc. Okay, very quickly, in terms of the technologies that we use, it's 3D scanning, recording. We do a lot of work with photography, film and video, virtual reality, augmented reality, mixed reality, digital fabrication, which is what I will spend a little more time looking at, which is 3D printing, CNC machining, etc. Regular digital printing. We do a lot of work around the analysis of materials, construction science lab, and the usual 3D kind of CAD capabilities. So we've got a range of technologies that we use and work with and support industry on. But with this particular topic, what I'm hoping to cover in terms of any learning aims is one particular around data capture, how we capture data and how we use that data. So it's an understanding, it's an insight, it's an overview of the different types of 3D data capture techniques that we use and their applications, understanding some of their benefits of these technologies, both in the built environment, relating to objects, components and parts through to architectural features, understanding some of the limitations of this technology, of scanning and of digital replication, understand some of the basic workflows that we go through, and some of the processes available for us to recreate and replicate objects, both for regular industry, architectural purposes, and some of the historical work that we get involved with as well. So I'll start off with scanners before I come on to 3D printers, because we're very interested in how we actually capture data, or we capture geometry. And we use a range of scanners that allow us to capture objects that are both the size of a button, right through up to a cathedral. So we regularly get involved with scanning that range of objects, which is a big range of objects. So for very small parts, using the kind of scanners that we've got below here that use either laser or structured white light, through to building scanners that can scan buildings, terrestrial laser scanners. So those marked in red are the types of scanners that we use. And I've broken them down into three categories: technologies that help to scan objects and features, technologies that help to scan structures, and technologies that help to scan landscapes. We don't do any aerial scanning or vehicle-based scanning, so I won't touch on that as much, but we certainly scan structures, and our preferred technology for that is using terrestrial laser scanning, photogrammetry, and a relatively new one called infrared digitization. There are other technologies out there that we are aware of, such as SLAM and GNSS, but they don't suit the type of work that we do. And the ones that I'm going to touch on tend to be the ones that industry use more than most. In terms of object scanning, we tend to favor structured white light scanning, laser scanning, and photogrammetry. And again, these scanners, depending on the size or the distance of the object, from a fraction of a meter to several kilometers, has an impact on accuracy as well. So when we're dealing with smaller objects, we can scan at a greater accuracy. And obviously that accuracy tends to dive away when you're scanning much bigger objects. But it's horses for courses to some extent. So that's roughly how we've look at the various scanning technologies that are currently available to us. And I've thrown in infrared because it's a relatively new one. Okay, so terrestrial laser-based scanning, if we're scanning buildings, yeah, we do a lot, like I said, in the heritage sector, but we also work with traditional structures as well, where we'll use a tripod-based terrestrial laser scanner. It's typically tripod-based, although we can use aerial drone, a drone with a camera attached to it to do photogrammetry and then merge the two data sets. But ostensibly, we're using a laser scanner where the device internally, it has a laser source that's bounced off a revolving mirror and it hits its object. So this box turns through 360 degrees and it also has a revolving mirror that turns it through another 360 degrees. So essentially, over in this top right corner here, you'll see a little black disc on the ground. That's the footprint of the scanner. And as it rotates, it throws out points, a laser beam. It then fires back to the scanner that we have. And essentially, the scanner records a point in space with an X, Y, and Z coordinate. And as the scanner fans out, you can see that these points become more dispersed. And we can control the density of those points dependent on the distance of the object and the quality that we want. But obviously, the more points to lay down, then the more memory that it eats into. And we do generate large data sets when scanning buildings, usually of from several gigabytes to many gigabytes in low terabytes. So it's very intensive in terms of the file size. But here you get an idea of how the scanner disperses those points to create points in space. The color definition here is that where it's green, the spot is good quality. Where it tends to be red, where the laser strikes a surface at an angle, then the data set is not as accurate when it's more perpendicular to the actual scanner, if that makes sense. But obviously, the more locations that you base the scanner, then the better the quality of the information. The scanners as well that we use can also pick up the color of an object. It's RGB signal, which means that we can create a full color set of a particular environment. So with terrestrial laser scanning, we're using it to measure that environment. We're using it to feed back to our architects or the architectural design process so that adjustments can be made to new models, to reinstatements of buildings, or for the development of extensions or outright new buildings. So this is why we're measuring that environment, to assess that environment, to bring into the CAD environment to help us develop the architectural model, or the intelligence of the architectural model, the information that we want to build into that, the building information model. So we use this as a core technique to create a high resolution 3D data set. Typically tripod mounted, but like I said, you can take coordinates from drone-based systems too and combine those into your point cloud model. The laser system, a terrestrial laser tripod-based scanner, it tends to be accurate or has an accuracy that architects will find acceptable for the kind of work that they're doing. And like I said, we can add into that texture and color signals, but it does create these intense data sets. We can also enable to improve accuracy, the GPS tracking of the position for the scanners, and we can refine that GPS track position as well, over and above normal the GPS signal. And we can also create these 360-degree views with the work that we do here. And equally, because it's laser-based, we can work in total darkness. And that is the beauty of a laser-based system that we use here. So that's what we would do. That's the type of technology that we use to sort of capture built structures, a built environment. Some of the applications that we use, primarily because of the way we work with industry, we do a lot of work across the country with architects, developers and constructions, particularly in the heritage environment. So in this case here, we're looking at a property where a lot of its timbers date from the Norman conquest period. And essentially, they were wanting to have this laser scanned, one, to understand the construction of the building, two, to virtually deconstruct it, and three, to understand the provenance of this structure, its historical importance. So the red dots here illustrate where we were able to position the scanner. There's no floorboards here, and so we can look straight through the scanner up into the roof joists, etc. And that's what we're trying to do. We're trying to scan it to create a model that we can deconstruct, analyze, and understand its importance. So we can take cross sections from it. We can create photogrammic elevations, and we can create these doll's house views that you can also work through too, and I'll come on to that one a bit more. This is typically one of the buildings we'll look at, which is a very early mud and stud building that the National Trust own, that we were using these techniques to help deconstruct that and understand its significance. And again, one of the key areas was to understand some of these timbers and to have these analysed to understand their dates, which we've pinned down that it was a tree that was grown in about 900 AD, and it was felled about 200 years later and used in a particular construction that we then have been able to show was reconstructed into this house. So a lot of these timbers here are from a tree grown 900 AD, felled just before the Norman Conquest, and then a structure was built that was then later repurposed for this house. So from the scan data, we're able to take these kind of views that are dimensionally accurate. It's not a photographic distortion, it's an accurate elevation. We can then vectorize them so that we've got details of the various planks within there. We can take measurements within the models, and we can do a number of things, a number of sections to dissect this to help produce this statement of significance that we've done there. So this is how we've used a scanning technology in a built environment context. So that's what we have there. And again, we're regularly asked to use this on historical properties, where we'll scan it, analyze it to produce these statements of significance, but also to produce these elevations that are dimensionally correct, dimensionally accurate. From there, you can then analyze it to an nth degree. If you wanted to pick out every stone in there, you could. You'd know that they'd be reasonably accurate. But equally, the architect, the curator, the owner, the custodian of this building can use that to monitor movement, can monitor wear and tear, and then can use that to help with any future innovations, etc., etc. They also use it for things like disaster recovery, and again, just to understand its importance. Another technique that we use, so what I've previously just very briefly touched on is terrestrial laser scanning. But there's another technique out there that will gain a lot more credence, a lot more credibility, and we will see its use grow, which is photogrammetry, where you use a really good digital SLR camera to take a series of pictures, either in parallel or in an arc, where software then looks at these images, can see that they're taken from different angles, and it's able to create the geometry from that. It creates a point cloud, it wraps texture to it, it then creates a polygon mesh that represents the surfaces that it's seen. We like this technique because it's very portable, unlike a terrestrial laser scanner that is not so portable. But the only downside with this is that you take the photos, you then have to take them back to a lab or to your laptop to upload them and to process them. And the software at the moment, the better software for this technique, it's expensive, it's quite time consuming, it's complex, but it does produce a good result to create a three-dimensional model. But it's a tool that we use. It complements terrestrial laser scanning very well, and you can take these aerial views if you strap a good digital SLR to a drone. So these are the images that were taken here. This is actually of an old Viking structure on Greenland, and again, photogrammetry was used because it's highly portable, whereas the terrestrial laser scanning that you have to take a series of laptops, you've got to take your scanners, you've got to take your targets, and targets are spherical balls. We usually take between half a dozen and a dozen of those, so it's a little bit more kit intensive, whereas photogrammetry, you could just be out in the field with a digital SLR and then take it back to base to do all the processing. So that is the one technique that we use, and this is how we've been using it with the applications that we have. Right, so I'm just going to refer you to another technique that is incredibly useful, incredibly popular at the moment, which is digital infrared scanning when it comes to the built environment. And we've worked with a number of organizations here, both heritage organizations, architects, constructors, manufacturers, where we've gone into either scan their showroom, scan their museum, scan a construction site to create what we call a doll's house view of an object, of a building. It's like Google Street View for the insides of a building. It's a camera that's about the size of a shoebox that fits onto a tripod that you can walk around into an environment and take these scans. I'll just dive inside the actual model. Hopefully it's not, because I'm doing this over the internet, it won't feel too clunky, but here you can see I can navigate through this. I can use a mobile phone, I can use a tablet, I could use a VR headset to navigate my way around this museum. In this case, this is some work we've done for the National Civil War Centre to scan the building, where we've then shown them how to add what we would call interactive hotspots, which can be just a simple label, or in this case, I think they've got an added to it, a YouTube talk by an historian, where this whole museum has now become a virtual museum for A-level students of history. And it's proved very useful for them in the periods of COVID, that you can access these spaces remotely, digitally, and more importantly, what we've encouraged them to do is to say that you've got new markets here. You've created an educational product that you could market to anybody that's teaching the A-level history syllabus, be it in the UK, of the four corners of the UK, or across the globe. Wherever that syllabus is taught, you've now can provide access to that. And these hotspots, most of them are talks and lectures by academics, providing information geared towards the A-level syllabus. So this is a technique to be aware of. It's getting easier to use. It's a very simple technology to use. You can create these environments using a smartphone, using your iPhone, using Android, but you tend to get a better result if you use their hardware, which isn't too expensive. It's about $2,500. And we use a mixture of hardware to help capture spaces. We use terrestrial laser scanners from Leica, as well as the Matterport system here to create these kinds of environments. So that's looking inside an interior. Then we have this doll's house view. We can identify that we want to look at one floor or two floors or all floors. And to scan this building probably took us no more than a day. We spent a couple of hours with the client teaching them on how to add these hotspots. They've then gone away and curated all these hotspots. So that is what we call virtual immersive environments. It's proved very useful for companies to create virtual showrooms. We've done a few virtual showrooms for people and created links through to their shops, etc. This is a shot of our own lab that we've used to help promote our lab. We've used it to help have remote meetings, minimize the cost of meetings, particularly if we're going to analyze a building that's on the Isle of Man, for example, which we've done in the last 12 months. We can add all these hotspot information. It's been useful for training and wayfinding, so people can get familiar with space before they have actually arrived at it. And you can take measurements in it, you can take photos in it, and it's just proved a really useful tool in these times of COVID, in times where you need to have remote access to spaces that are previously closed off. Okay, I've talked a lot about some of the techniques, or given a very brief taste and brief overview of the stuff that we use for the built environment. But when it comes to objects, components, artifacts, then we tend to work with structured white light scanning predominantly, because it's easy to use and the software is great. Structured white light, instead of firing a laser beam at an object where the scanner and the hardware sees a point in space, all these devices here, particularly these three on the right side here, not the left one. The left one is a laser-based one. But these use a series of lights, and they have a series of cameras on the front and a projector. And the projector pulses patterned light at an object that distorts when it hits that object. And then the cameras, positioned at different angles, sees a slightly different image from it. The software then knows that there's some geometry there, and it reconstructs that geometry. And its accuracy, with the machine on the far right here, goes down to 0.05 millimeters accuracy with that data. When you're scanning something the size of a piece of furniture or a car, then the accuracy slightly goes down to about 0.1 of a millimeter. So these devices are fairly accurate compared to a laser-based machine. They're also highly portable, particularly this machine. It's got no cables that tether it to a laptop, unlike the other three devices. So this is a great way for us to record objects and components, etc., etc. What all these technologies do, these scanning technologies do, the terrestrial laser scanners, the infrared systems, the white light systems, is it creates a polygon mesh that represents the surface that it's scanning. So here's a particular bust, and you can clearly see on here, hopefully you can clearly see on here, the tens of thousands, if not millions of points that have been triangulated. It's a polygon mesh that represents a surface. It's not precise geometry. And if any of you are engineers out there, then obviously you tend to deal with precise geometry. So scanning produces this representation. It includes an embedded color signal within there. And then we use this mesh representation to then either harvest as a template to create precise geometry, if we're dealing more with manufactured type components. And we use it for replication either through 3D printing, CNC machining, or whatever process is appropriate. And you can do some reverse engineering from this if you've got the right kind of software, but we tend not to have the demand to do the reverse engineering that much. We do it very occasionally. One example where we have reverse engineered something is where we've got a small electric motor and a gearbox, and we're just scanning the two ends of it because they need a particular component made in the center of it. So we scan those components to help us reconstruct some geometry for this here. This is a very simple project, a very simple example of where we've used scanning to create the distance between two objects so that we can then fill that in with the right component that then the client that we're working for then tools up for and produces the components that they need for this small motor and gearbox. One thing, again, that is common with a lot of these scanning processes, and it's important to us, and has a degree of importance depending on the object you're scanning that you're working with, is the assessment, the preparation to do the scanning. So if we're scanning a castle, then initially there's a lot of pre-tasks that we do before we actually scan a castle. So we'll meet with the client, we'll take lots of the architectural drawings that they may or may not have. We'll agree with the client where we need to position the scanner, and also we'll need to make sure that we've got access around a structure. So if we're asked to scan something in spring when things are beginning to grow or get overgrown, we might need vegetation cut back so that we can get all around access to structure. Likewise, if we're scanning an historical object, it often has to be done in a precise environment, usually under supervision of a conservatory, etc., such as this Roman tablet that we've got here. Where we've worked with building environments, it's around making sure that we've got the scaffolding in place and that we've got access to an element of the scene that we need to scan, and that some of the props are not in the way of what we're doing, and I can expand on that one in a bit. So we have to assess and plan any kind of scan that we do, even if it's a small object. We need to work out how we're going to get the scanner in there. And then we scan it, maybe with some calibration, we process the data, we create our digital asset, and then we need to work out how, with the client, how they want that data presented to them, because the data sets can be enormous. Benefits are scanning objects. So some of the benefits and opportunities that we use, and I've two examples here are heritage ones, but this applies if we're working with industrial components, is that a lot of the techniques we use is minimal contact and contamination. We can create this accurate digital record. We can do these digital repairs to objects, digital reconstructions. The heritage industry like it because they use it a lot for interpretation and things like disaster recovery, as well as being able to monitor movement, gross movement or minor movement, wear and tear as well, and collecting 3D evidence and reverse engineering applications. One example where we've used it is with the redevelopment of the hotel in Buxton, the Buxton Crescent, a very much a building that's had millions spent on it to redevelop this, but we got involved on a number of projects, but one in particular was this ceiling in the Blue Room. It's a cast iron ceiling rose in the middle, so which is I think it was about 2 meters in diameter. It was huge. It was causing the ceiling to bow, and then lots of this early embossed ceiling was coming down. The plaster was detaching from the lath. It was coming away, and they were losing this historically significant ceiling. And by accident, we got involved with this, where they needed to understand the historical background to this paper, its provenance, and we said we think we can fix this. We can recreate these ceiling tiles for you that will be authentic. So we scanned the ceiling we scanned the whole room, and then we scanned using handheld scanners individual tiles from the ceiling. We took away samples of the previous ceiling so that we could understand the formulation of the paper, formulation of the paints, and how we were going to reproduce the paper and the paints, because we do a lot of work with historical pigments. So we set about from the scan data to recreate a digital master, a digital pattern that we would then verify with the client, the conservation officer, and English Heritage. We produced a sample of the wallpaper here, of the embossed wallpaper, once we'd produced a male and female tool. And then from the first pattern that we produced, we took that along and we got the sign off on that so that we could be commissioned to then fill in the gaps, essentially. And that's the ceiling after we'd repaired it. We brought in a special plasterer to apply the plasterer, and then we applied the tiles to this. We redressed it, repainted it using paints that were historically accurate on a paper tile that was historically accurate. We even found out where the original paper came from. We found the original pattern book, the original manufacturer. That's part of the thing that we do, where we've got a conservation team on campus that spends all of its time working with industry. Okay, so I've talked about how we capture the world around us digitally, three-dimensionally, from tiny objects through to built structures. But then there's this thing called 3D printing, which we've all heard of. But what I quite like is one of the reasons why it's become really important technology, and it will only get its importance, its benefits, its capabilities are only going to grow. So traditionally, over the many years that we've manufactured items from 100,000 years ago up to about 1986, we could arguably say that it was through two processes: subtractive and forming. Either we'd take a billet of material and we'd remove something from it to create a shape, or we'd take some pliable material or liquid material and pour it into a mold to create a shape. And then in the early 70s, a process was the technique where in 1986, one of the first 3D printers was produced that created an object by growing a structure. Using digital data, it would grow usually via layers and layers and layers of material and object. And this is quite a profound way of making things. And its profoundness is only going to develop and have an impact on certain manufacturing industries more and more. Obviously, what 3D printing does, some of its greatest assets, its great benefits is it gives us great freedom to make complex shapes without the need for tooling or jigs. So historically, when you're making items such as a simple fruit bowl or a simple piece of furniture, these are now done. These items here have been explicitly produced without tooling, without jigs, without fixtures, on the idea that you choose your object, you print it, you pack it, you pass it on. Or as well, from an engineering point of view, it's really useful around part consolidation, all the sort of the downstream activities that come through, all the parts that have to be assembled, stocked, etc., and all the assembly processes that you have involved with that. This can now be simplified greatly into a single component and grown via 3D printer. So it gives us great design freedom. It allows us to create complex shapes and optimization as well in terms of part consolidation. Customization and low volume production is what 3D printing is currently good at. It's not very good at obviously high volume manufacture, but that is changing, where we're seeing things like networking of 3D printers to produce volume items. So we're seeing endeavors like that, as well as 3D printers themselves becoming faster to produce parts. And then 3D printing has had this knock-on and will continue to have this knock-on effect with processes and supply chains, where some organizations now are rethinking where they're going to locate the manufacturing of objects and items or products based on the fact that they're taking greater advantage of 3D printing. So for example, only recently, there's a UK company opened up where it's beginning to manufacture a lot more of its bike components in the UK than historically having them produced overseas, because it's a high value bike and they use 3D printing to produce the frame components, which we don't tend to do that much of anymore. We use 3D printing to help model concepts that we can discuss with clients, that clients can look at, that they get some feedback from their customers. It helps us sort of plan investments, plan the manufacturing, etc. And it also helps to get the design right first time. It helps to smooth out the design process, helps to get the design concept signed off earlier rather than later in the design process. And I'll come on to that in terms of how we've used it and advised companies on how it can benefit a design process, as well as just to produce a nice part. These are just some examples that 3D printing has been used in a slightly different way than normal in terms of fixings. So wooden components here that have got no machining on them. So they've thought carefully about how to reduce machining processes, assembly processes. It's made it easier to package by having effectively a customized clamp or a clamp that takes a particular size of component that's just then clamped together to form a structure to support a tabletop. So that's one application there around process consolidation, I suppose. It's been used to help reinvent garments, and interestingly, 3D printing as well. When you look at how thread is woven and then produced into a cloth that's then cut into a pattern, 3D printing is going back to the old chainmail method, where we're producing a complex shape with all these little hinges produced in one piece, because 3D printing can produce assembled components that can mechanically work together to produce this particular garment. And again, all the intricacies of each individual shape here becomes easier to manage via a digital process. And this was just an example that was used to create this particular dress. Bikes. We were seeing 3D printing in sort of really high value aerospace manufacturing industries, but it's permeating down into something that is relatively as simple as a mountain bike. Some of the structures here are 3D titanium components on commercially available bikes. So it is beginning to find its way into more slightly everyday items, albeit fairly expensive mountain bike, but not out the reach of everybody. So it's beginning to have this trickle down effect. it's been used in prosthetics and in the medical industry to provide as an alternative to casts, where you can scan an arm and then quickly produce a cast that fits, and it helps to vent and aerate the arm where plastic cast sometimes doesn't work. And again, other areas of prosthetics that it's been used for, as well as in the creative industries by various ceramicists, being able to take scan data, distort it to create new works of art. I just quite like the work of this guy, Michael Eden. You can also 3D print food, you can 3D print biological components, you can 3D print buildings, you can 3D print bridge structures, you can 3D, the material palette that you can put into these machines is growing. It will set to grow, where you can put foodstuffs in there. So you can 3D print your cutlery, and you can 3D print the contents that you put on the end of the fork or in the bowl. You can do that now. You can 3D print complex food structures that high-end confectioners and cake makers are beginning to use. And you can 3D print components, biological components that you can insert into the human body that will not be rejected by the human body because they're much more customized to the DNA of a particular patient. So again, this diversity is growing all the time here. We've been using it again in an array of industries, but particularly the heritage industry, where on this particular project, we were tasked to help interpret the decorative scheme, the previous decorative schemes of this room, so that the client could work out how they wanted to redecorate it. But also, we replaced some of the door finials that had gone missing from previous ones. So we scanned in one remaining door finial that they'd got. We 3D printed the substrate, and then we make it look like a marble plinth, a marble finial to go above the door. That's what we were able to do with the client there. We work with various museums where we take various antiquities. In this case, it's a marble, 1st century Roman bull found in somebody's garden. It's about 1.5 feet long. We worked with a professor of Roman antiquities to understand its provenance and what it might have looked like. And then the museum asked us if we could recreate the full artifact so that their visually impaired visitors could feel it. And they liked the fact that we could do this, which meant that the people with impairments weren't going to touch the original object. They didn't want anybody touching the original object. But by doing a reconstruction in a single color, then certain of its visitors can engage differently and feel the past, so to speak. So that's what we were able to do with that particular client. Again, working with industry, we've working with various clients to help develop construction products. In this case, just a various range of plastic accessories for the scaffold industry, using 3D printing to verify components before tooling's commissioned. We've used it with collectors, so a terracotta warrior collection where we were given 3 terracotta warriors, 2 of the bodies were broken and the head was missing. So we 3D scanned in 2 good heads, digitally created a unique 3rd head, 3D printed out the substrate for the new head. We do lots of tests with paints and pigments, etc., to try and mimic terracotta as best we can to be applied to an ABS 3D print. And then we produce new heads for them that they've taken on to an exhibition around the globe of these particular three warriors. But at least there's a new head that's been made for this exhibition. And that's one of the photographs from the exhibitions of the warriors with its horses, etc., etc. So our team concentrated on restoring all the horses, the bodies, etc., and we produced a head for them. So I'm beginning to sort of try and want to then go over the processes that we use or emphasize some of the things that have become important to us as we've sort of experimented more and more with scanning, printing, and this whole gambit around digital fabrication using digital tools. So we've got a whole bunch of capture technologies or data acquisition technologies where you can use a range of stuff, some of which are becoming simpler, cheaper, the hardware or the software to acquire and use, where you can scan objects with a phone, where you can scan in building interiors with something as simple as a smartphone to create, record some data. It's this process in the middle that adds value, the data processing, the modeling, where we're using it to help create and recreate something. But importantly, what we are doing is creating a digital asset. And this cannot be underestimated. We're trying to abandon words where we're creating a 3D model, we're using something in CAD. What we're doing by using these technologies, by using CAD, by using a variety of software and tools, is we're creating a digital asset. And when you see the rise of things like non-fungible tokens, which means there's a marketplace for selling and exchanging digital assets, you do have to bear in mind that you're creating something that has potentially a monetary value now. And that's what we're trying to educate some of our clients with, particularly around creating virtual museums or access to inaccessible places that could be monetized. So this is becoming very important. Create the creation of digital assets, where these digital assets will have both a value as a virtual application as well as a physical reinstatement or replication. So we're creating these screen-based visualizations, virtual modeling, virtual environments, we're augmenting them, and as well as creating replications, physical replications. And then in terms of using these technologies within the process of design and innovation, and the fact that the design and innovation as a process is incredibly important to businesses, in terms of if you get that design process right, it saves you so much more money down the line. The seeds of a good product start with design. The seeds of all your cost start with a good design. So we also work occasionally with companies where they're not interested necessarily in the technology. They want to get the process of design and innovation right using some of these new tools. So we often take a design process. Here I've greatly simplified it and divide it into rough two sections: the creative bit, the research, the brief, and the concept stage, to the implementation, where you're detailing something up and preparing it for production, and where these technologies fit in with that. And quite often, what we help companies with is this front end of this process, this fuzzy front end of the process, where you're trying to understand the problem, define the problem, so that you're better prepared to instruct your designers to come up with a good solution. And 3D printing has its place in this, because you can produce a physical item much sooner in the design process. And the big plus for that is that if you can 3D print something sooner in a design process, when it's cheaper, you've got a good opportunity to change your mind. But once you've committed to tooling, once you've committed to all the marketing infrastructure, the logistics infrastructure, and you want to change your mind further down the design stream, it's not only more expensive, it's exponentially more expensive. So we're encouraging the utilization of these digital tools, of the 3D printing, of prototype verification, of producing prototypes sooner, help the client, the customer, get involved in the design process sooner, so it's easier to change your mind and it's not as expensive to change your mind. And the other thing that I tend to do with companies as well is that the other thing as well that's really important is identifying the problem when we're working with companies. So for example, we worked with one company and it just asked us to do something really simple. It wanted to work with a group of product design students to create some new design decorations. And we were talking and having a chat about this, but then she sort of said that I'm only profitable for 3 months in the year. And I went, well, can't we have that problem to solve? That sounds like a far more important problem to solve than come up with a range of Christmas decorations. So what we proposed was to help that company develop a design service around working with, rather than individual customers, but working from a B2B point of view, a business to business point of view, help develop a service that you apply to retailers, to the tourism industry, to help decorate their environments and sort out the decoration and the management of that much sooner. And also there are many more festivals throughout the year. So why can't we help design your business to provide this service for the decoration, festivals decoration, essentially? So that's what we work with in there. So that's why I think sometimes you cannot underestimate, sometimes it's worth spending a little bit of time formulating a problem, researching a problem, because sometimes you might think it's over here when actually it's over there, and it's a very different shape. And it's going to give you a very, very different return as well if you identify the problem. So overall, in terms of the limitations of scanning, 3D printing, etc., from our own experience, is that scanning isn't always a non-contact process. You have to do a degree of handling. You have to be able to see the surfaces that you want recorded. You have to be able to see them all. These are all line of sight technologies. There's little guesstimation, although the software is getting better at guesstimating the holes or the points that it can't see. Access, whether it's a small object or a big object, how are we going to hold a small object for the scanner to see it? How are we going to get around a big object for us to place all the scanners to gather the data that we need? Do we need to do aerial scanning, etc., etc.? And sometimes that has health and safety issues if we're trying to scan something it's on the edge of a cliff or something, or if it's several meters up in the air where we need to get up in the air to point our scanners to it. Data and digital assets. We're only creating representations of the surface, not precise geometry for most of the projects that we work on, although you can do reverse engineering and it's getting easier. It used to be very expensive with the software and there weren't many choices when it came to reverse engineering software, but that has got better. It's also got better where that if you want to create a 3D print, you have to create what we call a watertight model as well. That used to be a big issue, but increasingly finding it's less of an issue as the software is getting smarter at finding holes and plugging those holes. If it's got a hole, then it's the 3D printer won't make it. It tends to fall over and keel over. It has to be watertight for it to make that geometry. Most importantly, though, is data management. How you plan to manage really large data sets and exchange that with the customer. So if we're scanning something, we want to preserve all that original data as best we can, but also we need to provide our client with access to see this data. So we use various platforms to do that, such as ViewShape, Sketchfab, as to help our clients have that immediate access to look at their data. Or we use the Matterport system to create these dolls houses of virtual immersive environments. Replication. When you 3D print something, you can get a loss of detail, particularly if you're using FDM type 3D printers, fusion deposition model printers. 3D printing at the lower end is using resin-based machines where the quality of the 3D print is becoming a lot better. And I think that will change. So there's always some loss of detail, but it's not as bad as it used to be, but do bear that in mind. Finishing is the big one. If you need to finish something, it's still a labor-intensive process, particularly when we're dealing with historical objects and we're trying to mimic a finish. It's a very labor-intensive process. Process and skill sets. One of the things that we really like, and the Buxton, the ceiling tiles that we produce there, is that quite often it's making sure that we're shifting from an analog mindset into a digital mindset. That with lots of these digital technologies, you can sometimes have the ability to reinvent the process, to reinvent how you might produce something or invent something. You could come up with a complete new business model to create a product and sell a product through 3D printing. That certainly happened. And again, the bike manufacturer is one example of that, where people are bringing the manufacture of shifting the base of where that's manufactured, and that's having an effect on their own business model, the way that they do business. So some of these technologies can be disruptive, and there's room for innovation in terms of how you create, design, produce, and sell objects. Whilst some of this hardware and software can be expensive, although a lot of it's shifting to a subscription-based model, it's making sure that you develop all the skills and join all the processes up, and give people the time usually to learn these and practice with these technologies to create a comprehensive process to produce something. So in summary, I've gone over a range of 3D print techniques, data capture techniques, very briefly looking at the workflow here in terms of capture, data manipulation, and the ways that we can output it with some examples, hopefully that's shown you how we've used it. I think that's it. So thank you very much. If you've got any questions, then please do fire away. I've got a feeling the host is somewhere in the background. But yes, if you've got any questions, then feel free to type them in or unmute yourselves and ask me, and we'll take it from there. Thank you very much.